All right, so chapter 12 is the title is Static Equilibrium and Elasticity. Okay, so before I get into the slides, let me tell you what this is about. So this is sort of two separate topics. They're mashed into one chapter. Just this portion will become a whole course if you do civil engineering or something like that. So this will become a whole course, and that's just based on two equations. Okay, so I'll show you that. I'll start off by illustrating that, and then we'll talk about elasticity. Okay, anyway, I'll go over those before. Okay, well, before I start that, what does the word equilibrium mean to you guys? What does equilibrium mean to you? Huh? Okay, so in our context, equilibrium means acceleration is zero. Okay. Now, does this imply velocity is zero? No. Very good. So it could be velocity is zero or velocity is constant. Okay. So acceleration equal to zero means velocity could be zero or velocity could be constant. Okay, so this, when acceleration is zero, it is in equilibrium. The object is in equilibrium. And when velocity is zero as well, then that means it's static equilibrium. Okay, this would be dynamic equilibrium. So for instance, when you're driving on 95 at constant velocity, you're in dynamic equilibrium. Okay. What object do you know is in static equilibrium? A bridge is in static equilibrium. What do you want the bridge to be in static equilibrium all the time? Okay, so our structures, we want to be in static equilibrium. Forces on our structures might change as cars and trucks drive over the bridge. Forces are changing. Do you want the bridge to move? No. I guess so. That'll be our interest, static equilibrium. Okay, so we want to make sure our structures are in static equilibrium. So let's start off with that example. All right, so here's an object. All right, no. So here's a point object. Okay, and I apply a force F1. Okay. So for that object to be at rest, what should be true?
Forces cancel out.
Yeah. So the sum of the forces should be equal to zero. Okay. So if for a point object, if you make sure that all the sum of all the forces acting on the object add up to zero, then the object will be in equilibrium. Okay, it won't accelerate. So the net force on it is zero and it won't accelerate. How about this object? Will this be at rest? Okay, so it seems like this condition is good for extended objects as well.
It goes for the center of that.
What's that?
It goes for the center of that.
All right. How about now? Okay, so it will still be at rest, but how about now? it will spin. Okay, so for extended objects, this condition is not sufficient. Okay. Why didn't it spin now? What was the difference between the two? Mm-hmm.
They have opposite,
Torques.
I was gonna say opposite cosines.
Well,
Directions they can.
okay, so this force will make the object rotate clockwise about this point, about the center of mass. This will make it rotate counterclockwise. They have the sum of the torques is 0. Okay. So for an extended object to be in equilibrium, those are the two conditions you need. You need the sum of the forces to be 0 and the sum of the torques of these forces to be 0. And those two equations are the basis of an entire course of statics. And that's static equilibrium. That's the first part of the chapter. Did you guys understand that? All right. Yep.
For dynamic equilibrium, it has to go in the same direction.
No, for dynamic equilibrium, it's not at rest. The angular velocity is constant and the linear velocity is constant.
But doesn't acceleration change when you change directions?
Right, so it can't be spinning. Yep. Okay. All right, so that's static equilibrium. For static equilibrium, you want the sum of the forces to be 0 and the sum of the torques to be 0. Okay? So that's what we want on our bridges and stuff like that. As forces change on, you don't want this building to shake with 100 people or 500 people and stuff like that. Yeah. All right, here's the static thing for elasticity. Now let's talk about this fella, elasticity. Okay, so here's a bridge and okay, so as vehicles go by, what happens to these cables? They stretch. Okay, and once the car goes away, what do you want this cable to do? To go back to its original shape. Exactly its original shape. That is elastic behavior. How long do you want it to do? Okay, so this car went by, the cable stretched, it went back to its original shape. Then the next car goes, it stretches. You want it to go back? Yep. How many times? Forever. But of course that won't happen. Okay. All right, so that's what you want, elastic behavior. Okay, so when this cable stretches, here's what happened. Here's the microscopic picture of those cables. Here are the atoms. The forces between atoms, you can think of them as modeled as springs. And when that cable is stretching, each of those springs are stretching, little springs. And when the car goes back, you want the spring to go back to its original shape. Okay? So if cracks develop and stuff like that, then it might not go back. Okay, so you don't want permanent deformation. Okay, so that's what we are interested in. We are interested in elastic behavior of our structures. You build a tall building, the wind will sway it, and then when it comes back, you want it to have its original shape. Yeah. All right, so those are the two things we'll be talking about. Now, in this example, okay, you saw that it was important to know where the force is acting, okay, because the torque will depend on where the force acts. Okay, so now one of the forces on an object is its weight. Okay, the force that Earth exerts on it, the force of gravity. You want to know where it acts, and the point where its weight acts is the center of gravity. Okay. So we'll start off the chapter with showing you how to find the center of gravity of an object. Okay. All right. So Now we know the two topics we'll be discussing: static equilibrium and elasticity. For extended objects, the two conditions for static equilibrium are the sum of the forces acting on an object should be zero, and the sum of the torques of these forces should be zero. Okay, so that's that, and we'll come to elasticity. Okay. All right, so here's an object, and okay, so this is the formula you saw for the center of mass for this object in the last chapter. Okay, so the center of mass was you break up the object into tiny pieces, m1 times the x coordinate plus m2 times the x coordinate, and so on, divided by the total mass gives you the center of mass. Now, if you wanted to find the center of gravity, what you would have to do is you do the same formula except that add acceleration due to gravity at that point. Acceleration due to gravity at this point. Okay. And then divide by the weight of each of those masses. Okay. So now let me illustrate the difference between these two formulas. What is the acceleration due to gravity here at this point? I'm sorry? How about here? On top of the building? 100 meters from here? On top of Mount Everest? Huh? Less than 9.8. Okay. So, if your structure is large, then the center of gravity will be different than the center of mass. For most man-made structures, the center of gravity and the center of mass are the same. Okay? So unless your structure is 10 miles, 20 miles tall and stuff like that, then the center of gravity will be different. Okay? So for Mount Everest, center of gravity is slightly below its center of mass. Okay? But as far as we're concerned, we'll always take center of mass and center of gravity to be the same. We refer to center of gravity because that is where the weight of the object acts. Okay? Remember, when you're calculating the torques, you need to know where the weight of an object acts, where the forces act. So center of gravity is the point at which its weight acts. And so for most uniformly shaped objects, the center of gravity is at the geometric center. Okay. All right, so we'll be interested in problems like, you're climbing the ladder, and of course you don't want the ladder to slip. And so we'll analyze all the forces, okay? So let's say we put you on the ladder there, okay? And so this is the wall pushing on the ladder, okay? So normally we always assume that we're leaning against a smooth wall, okay? Later on in your junior and senior classes, you might lean it against a rough wall, and then there might be friction forces there as well. So there you are on the ladder. There's your weight. There's the weight of the ladder. There's the normal force that the ground exerts. And there's the friction force. This is a static friction force. Well, you hope it's a static friction force because you don't want the ladder sliding, right? If the ladder were sliding, then it becomes a kinetic friction force. Yeah? So this is the force preventing it from sliding. And that's why you have a thick, nice rubber boot on the ladder, okay? So that this can be as large as you want to prevent it from sliding. Okay? All right, so anyway, we'll analyze problems like this. Okay, so center of gravity is the point at which the weight of the object acts. Okay? And for our purposes, we'll take that to be the geometric center. Okay? This is just a fun picture. You can see that, so these are all uniform slabs of equal masses and stuff like that. And you can see that this slab is way beyond the edge of this table. Okay? And you can go home and try doing that with Jenga tiles. So how's this possible? All right, so for instance, if our phone dies, then we don't care, right? All right, so when will it tip over?
Past the center.
What?
Past the center of gravity.
When the center of gravity is past the edge, okay, that's when it will tip over. Okay? So as long as the center of gravity is on the beyond the edge, then it won't tip over, and that's what's happening. So here, you see the center of gravity of this guy of the top slab is there, and that is on the left of the edge. The center of gravity of these two guys is there, that's behind the edge. The center of gravity of these three guys is there behind the edge. Okay, and so on. So as long as the center of gravity of these guys, is behind the edge, then you're good. Okay. See that building? Okay. So, you can build structures like that as long as the center of gravity of this guy is behind the edge, you're good. Okay. So you can see a lot of buildings like this. There's a nice picture. Okay. This object is in static equilibrium. The center of gravity is above the footprint. Okay, you saw that. Yeah. All right, so you saw the two conditions for equilibrium on an extended object. For an extended object, the sum of the forces acting on the object should be zero, and the sum of the torques acting on the object should be zero. Okay, so in this situation, for this object, there's a force in that direction and the weight of these two guys. The sum of these forces is zero. And if you calculate the torques about this point, this has zero torque, and this guy and this guy is a clockwise torque, and this guy is a counterclockwise torque. Okay. Are these guys all of equal weight? No, of course not. Okay. So this, you guys have been on a seesaw. If you're closer to the fulcrum, you're heavier. Okay. So let's sort of figure out the weight of these guys. Okay. So let's say this is x and this is 3x. X and 3x. So the torque of this guy will be, so let's say this is m, and m times 3x, you multiply mg times 3x, should equal this mass times x. So m is 3m. So this guy weighs 3m. Now this whole thing weighs 4m. So 4m times 3x should equal m2 times x. m2 is 12m. Now, how much does this whole thing weigh? Oops. So this is 12, 15, 16m. This thing weighs 16m. So 16m times 3x, 16m times 3x should equal m1 times x. So this guy weighs 48. Pretty slick. I mean, so an artist making this, you might have seen art pieces like this in front of buildings, various buildings and stuff like that. So even though they might look the same, this guy is 48 times heavier than this guy. Yeah. All right, anyway, so for extended objects to be in static equilibrium, these two conditions should be satisfied. Okay? All right. Now, right now we'll keep things simple. So most of the forces, all the forces will be in a plane. So they'll only have x and y components. So these will be the two conditions. The x components should add up to 0 and the y components should add up to 0. And when forces are in a plane, the torque is in the perpendicular direction. So it'll have only a z component. Okay? So we will solve problems where these three conditions will need to be satisfied. So if you have three equations, then how many unknowns can you solve for? 3. Okay, so if you have three equations, you can solve for 3 unknowns. Okay, so those are the kinds of problems we'll solve for. All right, so here's a typical problem. Okay, so here's a plank, and here's scaffold at a construction site, and this guy wants to be able to walk back and forth without the cable breaking. And as he's walking back and forth, the tension in the cable changes, so the forces are changing, and you want the structure to be in static equilibrium. Okay, so that's the kind of stuff you will be putting weights in there and all that kind of stuff. Okay, so your job will be to calculate what would be the maximum tension that this cable would bear, and then of course to factor safety into it, what do? You buy a cable twice as strong. You don't want to get sued, right? So this is the kind of stuff we'll analyze. Okay, so what we'll do is we'll draw a free body diagram. Okay, so let's see what this means. Okay, so what is it that you want in this problem? What's your goal? What? Yeah, okay, so yeah, that's one of the goals, but so you want the scaffold to be at rest. You want the scaffold to be in static equilibrium. So let's look at all the forces on the scaffold. So you want this fellow to be at rest. Okay, there's the tension in the cable. There's the weight of the board itself. There's the weight of the person. And what is this guy? Right, so you see this guy is pushing the scaffold into the wall, and that's the reaction force of the scaffold, of the wall on the scaffold. Okay, so a free body diagram, what we're doing is we are only drawing the object that is of interest to us. Okay, we want the scaffold to be at rest, so that's all we drew. We didn't draw anything else. Okay, and then we drew all the forces on the scaffold. What's your goal? For that to be at rest. So, and the two conditions for that to be at rest. What are the two conditions? The sum of all the forces should add up to 0, and the sum of all the torque should add up to 0. Okay. Now here's the trick. Okay, so the torque of this force, the torque of any force depends on what point you calculate the torque about. Okay, for instance, the torque of this force is 0 about this point, but it's not 0 about this point. So what point do I calculate the torque about? What's that? So it turns out that if the sum of the torques is 0, then it doesn't matter what point you calculate it about. Okay, you can calculate the torques about any point, and it'll always come out 0. So then what do you do? You calculate it about the most convenient point. So if you if in your problem you're not concerned about this force, you're not solving for this force, calculate the torque about that force. Okay? And then that's one less variable you have to worry about. Okay? So when the sum of the torques is 0, then you can calculate it at about any point. And so you pick a convenient point. All right, so here is the free body diagram, and we'll be doing this kind of stuff. Okay? So choose a convenient axis for calculating the torque of an object. When the net torque is 0, the choice of axis is arbitrary. Okay? So a force, when the torque is 0, you can calculate the torque about any point and it'll still be 0. Okay. A force that acts along a line passing through the axis produces 0 torque. Okay. So for instance, in this picture, what we have done is, if you're calculating the torque about this point, let's say, you see what we have done is we've broken this force into that component and this component, and the reason we did that is because this component will have 0 torque. It's passing through the axis. And the moment arm of this guy is easy to calculate. It's just this length. Okay? So oftentimes you break up a force into components which are convenient. Okay? Of course, if you were calculating the torque about this point for some crazy reason, then this decomposition wouldn't be of any use to you. Okay? But we won't be doing that. All right. So here's another problem. So let's say you're bowling and you're getting ready to roll. So here your arm is at rest, and here are all the forces on your arm, on this bone. Okay, so let's look at the forces on this bone. There's the weight of the ball, there's the tension in this muscle, and this bone is pushing down on this arm. So there are those 3 forces acting on this bone. And again, if your arm is at rest, then the sum of these forces must be 0, and the torques of these forces must be 0. So let's say we calculate the torque about this point. By the way, this should be right there. That force should be right there. Okay, so let's calculate the torque about this point. This guy will have 0 torque. And this is the moment arm for this force, and that is the moment arm for this force. Okay, so now that's so in general, if this is x, this will be about 15x, depending on how tall you are and all that stuff. Okay. So this force, the moment arm is 15x. For this force, the moment arm is x. So that's a clockwise torque. So that would be mg, clockwise torques are negative, times 15x plus f times x should equal 0. Okay, the tension in your muscle, what is this saying? Is 15 times the weight of this bowling ball. Whoa. Sounds like a pretty bad design, right? To lift a 15-pound bowling ball, your muscles are exerting a force of 225 pounds. What's going on? So muscles contract when they're applying forces. Okay, that's the thing. So you are willing to. Okay, so here's the thing. Work done is force times distance. Okay, so since your muscles, like Sophia said, since your muscles can only contract a small distance, they're designed to apply large forces. Okay, because your muscles are contracting by some sort of protein molecules like this. So this goes into this protein molecule. Anyway, so they're stretching and contracting very little, and so that's why they're able to bear large forces. Okay. So for instance, if you stand on your tippy toe like this, your Achilles tendon is bearing 4 times your body weight. Stuff like that. Yep. All right, so let's climb ladders now. Okay, so here's a ladder leaning against a wall. We'll have it lean against a smooth wall, so this wall only exerts a normal force, a perpendicular force like that. There's the normal force the ground is exerting, and there's the static friction force, there's the weight of the ladder. Okay, so if the ladder is to be in equilibrium, the sum of these forces should be 0, and the torques of these forces about any point should be 0. Okay. So again, so if you don't want the ladder to slip, you spend a few extra dollars on a nice rubber boot there. All right, now let's come to elasticity. Yep. Yep. Do you have a question?
No.
Comment?
No, we get it. Sorry.
Okay. All right, now let's come to elasticity. Okay, so here's a structure, and let's say you applied forces like this. These are called tensile forces. Force is called a tensile force if it's stretching the object, and it's called a compressive force if it's trying to compress the object. All right, so let me see what your intuition is. And again, I wouldn't have been able to guess before I learned this. Okay, so let's say this is a concrete pillar. Let's say I apply 1,000 pounds like this or 1,000 pounds like this. When do you think it'll break? The pull will break? Yeah, that's correct. So it is weaker under tensile forces and stronger under compressive forces. It turns out that concrete is 10 times stronger under compressive forces than tensile forces. Okay, so let's, so compressive strength, the strength just means what is the maximum force that can break it. So for concrete, look at that. It's 10 times stronger than tensile strength. Okay, why is this table important? So once you see this table, what you want to do is make sure is that if you're using a concrete structure, you want to make sure that the largest forces are always compressive. You can apply small tensile forces, but large forces, you always want them to be compressive. Okay? And that's what's gone into this design. All right, so I'll give a very simple example, and I think I've talked about this before, but nevertheless, let's talk about it again. Okay, so let's say what has been incorporated in that design is that the large forces need to be compressive. Small forces can be tensile forces. Okay. And then what do? You want to hang a road. There's your road. Okay, so let's say the weight of the road, and how do you do when you analyze this situation? What is it that you do? So you're a civil engineer. What is it that you want to do?
You want the road to get static equilibrium.
Yes, and you want to analyze the worst case scenario. So what do? You just park fully loaded semis back to back, bumper to bumper. Okay? And then we'll analyze the situation. So let's say you're supporting 1,000,000 pounds. Okay, just making up numbers. And then, again, to make it simple, I have 1,000 cables, 1,000 of these cables. So what is the load each cable is bearing? 1,000 pounds. So each cable is stretched 1,000 pounds. And when the semis go away, what happens? The cables go back to their original shape. This cable, what is it doing? It's pulling it that way, and this is lifting. This guy is pulling on him, so that turns into, so all the pulls of these guys turns into a pull like that. Okay, this cable is pulling him, this cable is pulling him, and that turns into a compressive force on this guy. This tensile force is 1,000 pounds. How much is this guy? Very good. So that turned into 500,000 pounds. I mean, that has to be 500,000 pounds. Okay, so that was what this design was about. Tensile, small forces are tensile forces, large forces are compressive forces. Okay, and what this design let you do is build a bridge that is tall so you can have ships going underneath it with very little material. Okay, so that's what you did. All right, so now let's look at elasticity a little closer. Okay. So here's this rod. You apply a tensile force on it and it stretches a little. And of course, if it's exhibiting elastic behavior, once this tensile force is removed, it will go back to its original shape. Okay. Now the question is, how did it decide how much to stretch and then stop? So for instance, if you did this, if you applied twice the force, then it would stretch twice as much. Okay, it's like a rubber band. It's exhibiting linear behavior. How does it decide how much to stretch? Okay, so here's what's happening microscopically. Okay, so here's a layer of atoms. And here's the next layer of atoms. Okay, so there's the rod. And then I apply a 100-pound force on it. What happens? All these springs stretched when I applied the 100-pound force. And what are these guys doing? They're pulling back in this direction. These guys are pulling these atoms back in this direction. Okay, and these forces have to add up to 100 pounds. That's how much it stretches. Okay, the spring stretches enough such that these forces added up to 100 pounds. When applied 200 pounds, these springs will stretch more such that all those forces add up to 100 pounds. Okay, so how much stretch happens is the internal forces have to balance the external force, and that's what decides how much it'll stretch. Okay? And so once you remove this external stressing force, that stress will go back. Okay, the stretch will go back to its original equilibrium position. Okay. All right, so in our structures, that's what we want. We'll have stressing forces. The object will deform, and then when we let go of the stretch, we want it to go back to its original shape. Okay. How many times? 1,000,000 times, 1,000,000,000 times. Okay. And so on. The longer it goes back, the longer time your structure will last. Okay. All right, so of course, when you use all kinds of construction material, you want to know these properties. And, a material scientist does measure all these properties in labs, and you'll have tables like that. Okay. For marble is, it's a lot of microcrystals, and every block of marble is different, so tensile strength is hard to measure. Okay, well, it's not hard to measure, it's just that it's very variable, so you can't put it on a table. Again, your bone is also stronger under compressive stresses than tensile stresses. And bar like this, see the top portion is under tensile stress, the top portion is stretched, and the bottom portion is compressed. So if this bar develops cracks, it'll develop cracks over here. Okay. So similarly, on a bridge, when a truck goes by, when it buckles, that is where it stretches more, and so when cracks develop on a bridge, it'll be at the bottom. Okay. And so we'll talk about how to fix that problem, how to address that problem. Okay. All right, so there's a couple of terms we want to learn: stress and strain. Okay. Stress is due to the forces you apply on the object, and strain is a measure of the deformation. Strain is a measure of the deformation. Okay. So here a compressive force is applied, and this was the original volume, and you see here's the final volume. Okay, so strain is related to the deformation, and stress is related to the deforming forces you apply. Okay. So stress equal to the external force acting on the object per unit area. So force divided by the area is stress. Okay. An elastic modulus is defined as the ratio of stress to strain. Okay. And we want to study 3 different kinds of elastic moduli. Okay. And we'll come to that. So the elastic modulus of a material measures the stiffness of the material. Greater the modulus, harder it is to deform the object made of that material. So greater this number, for a given stress, the strain is smaller. This deformation is smaller. Okay. So for instance, what do you think? Does steel have a greater elastic modulus than, or steel or aluminum, which has the greater elastic modulus? Steel. It would deform less. Tungsten and steel? Tungsten. Okay. So greater the elastic modulus, harder it is to deform that material. Okay. So we talk about 3 types of elastic moduli we consider. Okay, so let's say you apply a force like this, then this face will deform relative to that face. Okay. So you can do this to a book, for instance, and you can easily see the deformation. Okay. This is called a shear modulus. Okay. So we'll consider 3 kinds of. Young's modulus measures the resistance of a solid to changes in its length. Okay, so when you're stretching an object. Shear modulus measures the resistance of deformation, shearing of parallel planes with relative to the solid. So how much can you move this top surface relative to the bottom surface? Okay, so there is the deformation. Bulk modulus measures the resistance of solids and liquids to changes in volume. See, this is bulk modulus. Okay, so you're compressing this object. All right, so let's consider tensile strain. Okay, so you apply this force, and the length of this object changes. Okay. So tensile stress is the force you applied divided by the area of cross section. Okay. Stress is force per unit area. And tensile strain is the length of this object divided by the original length of the object. So this is the percentage change in length. Okay. And this, you see, this is dimensionless. So the units of this guy are force per unit area, Newton per meter square. Okay. The units of pressure are also that, Newton per meter square, and you call them pascals. But in modulus, in elastic moduli, we just call them Newton per meter square. We don't call them pascals. Okay? All right, when this stretches, does anything happen to the cross-sectional area? Well, the volume doesn't change, so the cross-sectional area should decrease. Yep, right? That's how you make a wire thin. You pull it through a small hole and. All right, so the area decreases. Why aren't we talking about that? Well, the area will decrease a lot less than this length. Okay, the change in length is noticeable. So we're going to look at the largest dimension. Okay, so that's why we're talking about this. Okay, so the change in length, that's the most noticeable deformation. Okay. So you'll have curves like this for materials, for different materials. Okay, what is it that you want in your structures? You apply a tensile stress. When you let go, you want it to go back to its original shape. Okay, so you want elastic behavior. And so here's a graph for this some material. This is the stress you apply, this is the strain. Okay, so what this proportional limit means is if you apply a stress, anything below this, you apply the stress, it will stretch that much, it will strain that much, but if you remove the stress, it will go back to its original shape. That's the proportional limit. Once you apply a stress beyond that, it deforms permanently. Now you don't want that happening on your cable on your bridge, right? So what is it that you want to make sure? That when on your bridge you park semis, fully loaded semis, this is the maximum stress each cable bears, okay, and then you're safe. Okay, this is the yield point. Yield point is beyond that point, it's permanently deformed. Okay. And then it's a nonlinear behavior. This is a fracture point, it breaks. Okay. All right, so these kinds of graphs are useful because, this is where you want to live on your structures. Okay. Okay, so shearing modulus, when you're cutting something with a pair of scissors, what you're doing is you're sliding this plane and these planes in opposite direction, and eventually that shears off. Okay, so that's what you're doing when so this blade is applying a force parallel to that face, and this blade is applying a force parallel to that blade. Okay. So shear stress is force per unit area, and the deformation is measured up by how much did this face move relative to this face and how far apart they are. So delta x divided by h. Okay, the further apart they are, the greater will be this distance deformation. Okay, so that's the shearing strain. Yep. Bulk modulus. So here's this force you apply perpendicular to the face, and the volume of this object decreased. Okay, so bulk modulus is volume stress over volume strain. So bulk modulus stress is force divided by area, and this is the change in volume divided by volume, change in volume divided by the original volume. What is this negative sign doing there? Be more specific. What's happening to the volume? It's decreasing, so delta V is negative. Negative of negative makes it positive. Okay. Have you guys put a bottle of water in the freezer? and the bottle bursts. Okay, so when water freezes, its volume increases by 9%. You would need a tremendous force to decrease that volume by 9%. Okay. So most objects can't hold it. And, put a soda can, a beer bottle or water bottle, and the bottle will pop. Okay, and they use that kind of stuff in quarrying. So if you lived in a place that was cold enough where water froze overnight, what you could do is, let's say here was a mountain and you wanted to cut off this slab, what you do is you make a groove like that, fill it with water overnight, and when the water freezes, it'll push the slab up. The forces would be that great. Okay. All right. So here again, these all these values are useful, and so people measure these guys, these moduli for various material, and here are the numbers. Okay, so we'll see these numbers when we solve problems. Okay. So here's a problem that's solved. Okay, so here's a bridge that was built the old-fashioned way, and when vehicles go by, it buckles a little, and eventually the bridge, because this portion is being stretched, it's under tensile stress, you develop cracks in the bottom. So the question was, how do you fix this problem? So here's the solution. So this was steel reinforced concrete, and this was stronger than that, but still this is also buckling, and that would still eventually crack. Okay, so this is pre-stressed concrete. What that means is the following. You take these metal bars, stretch them out on a vise, and then pour concrete on top of that. Let the concrete cure, and then let go of this tension. What happened when you let go of this tension? It compressed, permanently compressed. Okay, now when your truck goes, when it's stretching, all it's doing is going back to its original shape. Okay, so now it's gotten stronger. All right. All right, guys, so that